Every time we toss a coin in the air, we know it's going to come back. All thanks to gravity. Gravity, responsible for our existence and the formation of the solar system in the first place, despite its universality, is the most mysterious force in the universe. Scientists have been testing the source of it for years, but now researchers are performing a study that's going to change everything about our understanding of the universe forever. They claim to have unraveled the real source of gravity. Join us in today's video to find out how this study is going, and how it's going to change our understanding of the cosmos, and how it's the answer to our creation. Gravity is one of the four fundamental forces that act upon us every day and steers objects with mass. The other three are electromagnetism and the strong and weak nuclear forces. These other three forces were entirely unknown to humanity until recent centuries, but gravity, which affects everything from sand grains to planets and stars, has long been the subject of speculation. It provides the force that keeps us on the surface of the Earth and keeps the Earth in orbit around the Sun. The Sun's gravitational attraction, which pulls all of its constituent elements tightly together, enables nuclear fusion, which produces heat and light. Or, in short, gravity gives life. In an effort to understand the world, early intellectuals developed their own theories regarding why objects fall towards the ground. But it would take Newton's moment of insight to convert gravity from an illogical tendency of objects to a quantifiable and foreseeable phenomenon. The simple definition of gravity defines it as the force that attracts a body towards the center of the Earth or towards any other physical body having mass. The British mathematician and physicist Isaac Newton is known for saying that he had no theories about how gravity operated. Instead, he used the notion that gravity was universal, that the same force that caused an apple to fall from a tree also kept the moon in orbit, as his starting point for explaining it in action. In his famous 1687 treatise, Philosophiae Naturalis Principia Mathematica, commonly known as the Mathematical Principles of Natural Philosophy, Newton described that the pull of gravity can be calculated by multiplying together the masses of the two objects and then dividing by the square of the distance between them. So, the attractive force of gravity goes up as either of the object's masses increases or as they get closer together. If we put numbers to this, doubling the mass of one object makes its pull twice as strong. And bringing two objects twice as close quadruples their mutual tug. These concepts were condensed into Newton's general law of gravitation. It's usually written as Fg equals g, in parentheses m1, m2, end parentheses, /r2. Newton's description of gravity was accurate enough to determine the existence of Neptune in the middle of the 1800s before anyone could even see it. But Newton's law isn't perfect. Astronomers discovered in the 1800s that there was a tiny discrepancy between Newton's law and the laws of nature when they saw that the ellipse formed by Mercury's orbit was rotating around the Sun faster than predicted by Newton's theory. This puzzle was solved by the German-American physicist Albert Einstein. In his theory of general relativity, published in 1915, Einstein suggested that the shape of space-time is what gives rise to the force we experience as gravity. All objects with mass, like our Earth, actually bend and curve the fabric of the universe, that is, space-time. And the curvature is what we feel as gravity. Even rays of light, which must follow this curvature, are bent by extremely massive objects. Einstein's field equations of general relativity, a set of equations that show how matter and energy warp spacetime, gained recognition when they accurately anticipated the changes in Mercury's orbit and the bending of starlight around the Sun during a 1919 solar eclipse. So, does it mean that Einstein proved Newton wrong? According to Science Focus, Newton's approach was descriptive. He matched an observed phenomenon to a straightforward mathematical question. Although his mathematics don't explain how gravity functions, it was, and still is, a remarkably effective way to describe how common objects behave. What Einstein accomplished was to advance our knowledge of the origins of the gravitational pull. The existence of black holes has been the subject of speculation using Einstein's ideas. In the vicinity of a black hole, Newton's law of universal gravitation no longer accurately describes how objects move, but rather Einstein's tensor field equations take precedence. Since then, astronomers have found actual black holes in outer space and have even managed to take a picture of the gigantic one that resides at the very center of our galaxy. Other telescopes have observed the influence of black holes around the cosmos. Astronomers have tested Einstein's theory with the help of these black holes. Scientists were of the view that they might find violations of general relativity. Many things were explained by Albert Einstein, but perhaps not black holes. The elegant model of gravity outlined in Einstein's general theory of relativity is thought to break down as the rules of the universe collapse in on themselves amid the dark depths of these enormous astronomical objects. In a study published in the journal Science, astronomers investigated the supermassive black hole Sagittarius A at the center of our Milky Way galaxy. The study shows that gravity behaves exactly as Einstein predicted, even at the extreme edge of a black hole, using Sagittarius A as an example. However, the study is only the first shot in a broad investigation to determine where the Einstein model breaks down. Study co-author Jessica Liu, an astrophysicist at the University of California, Berkeley, said, "We now have the technological capacity to test gravitational theories in ways that we've never been able to test before. Einstein's theory of gravity is definitely in our crosshairs." The scientists monitored the star SO2 in 2018, when it made the closest approach to Sagittarius A during its 16-year orbit. The star got as close as 120 astronomical units from the black hole, traveling as fast as 2.7% the speed of light. The astronomers used the Keck Observatory, Gemini Observatory, and Subaru telescope in Hawaii to track SO2's complete orbit in 3D. This data was paired with measurements that they had taken during the previous 24 years. If Einstein was right, the black hole would warp spacetime in a way that extended the wavelength of light from S0 to 2. In short, the waves would become longer as the black hole's strong gravitational pull drained their energy, changing the color of the starlight from blue to red. The fact that the star was still emitting blue light would support Newton's theory of gravity, which ignores the curvature of space and time. It would have suggested a completely different notion of gravity if it had changed hue. However, just as Einstein predicted, the star glowed red. Researchers analyzed a general relativity prediction known as the Gravitational Redshift, which states that light can be affected by gravity. Study lead author Tuan Do, an astrophysicist at the University of California, Los Angeles, told Space.com, "These measurements signal the start of an era where we can finally test the nature of gravity, using the orbits of stars around the supermassive black hole at the center of our galaxy." This has been long anticipated theoretically, but it's really exciting that we can finally do it. This is a milestone on the path to the future. More powerful tests of general relativity and other theories of gravity. The investigation into S02 is the first of many general relativity studies that researchers intend to carry out on stars close to Sagittarius A. One such target is S0-102, which takes 11.5 years to complete one orbit of more than 3,000 stars that are close to the supermassive black hole. As a result of the study, Andrea Ghez, a co-lead author of the Research and Astronomy professor at the University of California, Los Angeles, said in a statement, "Our observations are consistent with Einstein's theory of general relativity. However, his theory is definitely showing vulnerability. It cannot fully explain gravity inside of a black hole. And at some point, we will need to move beyond Einstein's theory to a more comprehensive theory of gravity that explains what a black hole is. Scientists know that at some point in a black hole, Einstein's theory stops working." And also, Kip Thorne, a Nobel Prize-winning theoretical physicist at the California Institute of Technology, said, The curvature of spacetime is so extreme that Einstein's general relativity fails. We don't understand how it works when the thing you're dealing with is extreme. Scientists are planning to use a new generation of high-powered instruments to conduct more tests of gravity around black holes. Lou said that in the next 10 years, we should be able to push Einstein's theory of gravity to its limits and hopefully start to see cracks. This will be a revolution in the field of physics. It's extremely difficult to foresee how recent advances in fundamental physics might affect our daily lives. The origin of our own universe and how we arrived at the current location nearly 14 billion years later might be explained by a new theory of gravity, though. What do you think about this? How is this going to change our understanding of the universe? Let us know in the comment section below. If you like this video, do give it a thumbs up and also maybe subscribe to the channel for more. Later.